Envision an inductor represented by its inductance L, connected to a current source. You've also got a handy voltmeter to measure the voltage drop across this inductor. The question now is, how can we decipher the current flowing through this inductor, solely based on its voltage? Let's kick things off with the equation that relates the voltage across an inductor to the rate of change of the current passing through it, where voltage is equal to the inductance multiplied by the rate of change of current. Check out our video on voltage across an inductor for more details on this. By shuffling this equation around, we can make the current the subject. Now, to find the current as a function of time, we integrate both sides with respect to time, which gets rid of the dt term on the left side. Next, we set limits on the integral on the right side. The limits in this case are time equals 0 to time equals t. As we also need to account for the current till time equal to 0, we need to add a term, I of 0, which captures any current that existed before our point of reference. We can also bring out the 1 over L term out as it is not dependent on time. Looking closely at our equation, a few significant insights become clear. 1. Influence of voltage. The integral term V of t over L dt suggests that the current's behavior over time is closely tied to the entire history of the voltage across the inductor. This isn't just about a momentary voltage value, it's about the cumulative effect of voltage over time. 2. Inductance as a modulator. The inductance, L, acts like a modulator or a dampener. Larger inductances make the current change more slowly in response to a given voltage, implying that the inductor resists rapid changes in current. Conversely, a smaller inductance allows the current to change more swiftly. 3. Constant voltage implication. If the voltage across the inductor is constant, the current will increase or decrease linearly over time. If it's 0, the current remains constant, affirming the inductor's nature to oppose changes in current flow. Okay, now that we have a bit of the theory covered, let's consider a scenario in which the voltage across our inductor follows the pattern displayed here. Starting at 0 volts, it linearly rises to 5 volts in 2 seconds. The voltage during this time period is given by this equation. The voltage is then maintained at 5 volts for 2 seconds, and then drops back to 0 volts over the next 2 seconds as defined by this equation. Given this voltage profile, our objective is to determine the current through the inductor at different points in time. We'll use our derived equation for this purpose. We will now find the solution in 3 phases. Phase 1 is the initial 2 seconds. The voltage is increasing linearly. We will assume that I of 0 is at 0 amps. Next, we find the integral of the voltage term. Now integrating over the time t equals 0 and t equals 2 seconds, we arrive at the following quadratic function for the current. Now plugging in the values for L and t, we can plot this current for the first 2 seconds as follows. Now let's move on to phase 2, from 2 to 4 seconds. The voltage is constant at 5 volts. Using our equation once again, we observe that the initial current I of 2 at t equals 2 is at 5 amps. As before, we plug in the voltage term for this section to our equation and find the integral which gives us the equation for current. We can now calculate the current over the period between t equals 2 to t equals 4 seconds. The result is a linear rise in the current, with a slope determined by the applied constant voltage divided by the inductance. Finally, let's move on to phase 3, from 4 to 6 seconds. The voltage drops linearly. We observe that the initial current, I of 4 at t equals 4 is at 15 amps. Next, we plug in the voltage term for this section to our equation and find the integral which gives us the following equation for current. Now integrating over the time t equals 4 and t equals 6 seconds, we arrive at the following quadratic function that shows the rate of current increase diminishes over time. By understanding the relationship between the voltage across an inductor and the current flowing through it, we're able to draw powerful insights and predict circuit behavior. We've seen today how integration becomes a key tool in this process, providing a clear picture of how current changes over time in response to a given voltage. I hope this video deepened your understanding of inductors and their behavior in circuits. If you found this informative, please give this video a thumbs up. Don't forget to hit that subscribe button and ring the notification bell so you never miss an update. Thank you for watching.